frequency of nonlinear oscillator. Consider Lagrangian, which we write as kinetic energy minus, and for the potential energy, we write it in terms of the familiar quadratic potential. But we don't stop there, and we keep writing, and we have cubic term, and then we will have quadratic term. Cubic term obviously gives us a symmetry. And note that this Lagrangian has no damping, obviously. And we would like to consider the motion in this nonlinear potential. The equation of motion can be readily found to give us x double dot plus omega naught squared x. And then we'll move nonlinear terms on the right-hand side, minus alpha x squared minus lambda x to the power 3. So these two parameters, alpha and lambda, will be nonlinearity parameters. Note that in order for motion to be stable for larger and larger amplitudes, we require that lambda to be positive. This equation is non-trivial to solve, because now we no longer expect just sines and cosines as our solutions. Such equations are often solved in physics by perturbation theory. The basic idea is that we will write dynamic variable x and frequency omega, which no longer is gonna simply be omega naught. We will write them as a power series of amplitude. We will denote the amplitude of oscillations as A. So what we are looking for is to write x as a function of time in terms of x1, which will be proportional to the first power of A, plus x2, which will be proportional to the second power of A, and so forth. Likewise, for frequencies, the true frequencies of oscillation, we expect to see a sum. The zeroth order frequency is just omega naught, the natural frequency, for oscillations with very small amplitude. Then we'll have omega 1, which will be frequency shift proportional to amplitude A, plus omega 2, and so forth. The actual perturbation theory, in this case, requires a number of steps. So in this overview, I will simply present the results. The first term of the perturbation theory is simply A times cosine omega t, where omega is given by this expression here, the true frequency, which itself has several terms, omega naught plus omega 1 plus omega 2 and so forth. The result for the first term of omega gives us 0. In other words, there is no shift in frequency, which will be linear with A. For the second term, x, we find that it will be given by alpha A squared divided by 2 omega naught squared plus alpha A squared divided by 6 omega naught squared times cosine 2 omega t. Couple of things worth mentioning. We see that asymmetric potential generates DC offset. And we also see that this term predicts oscillations will have second harmonic. This is the example of second harmonic generation. Incidentally, this is how nonlinear crystals work in lasers, where you shine a laser or one wavelength and you get light with doubled frequency. The second order term in frequency is given by 3 lambda divided by 8 omega naught minus 5 alpha squared divided by 12 omega naught to the third power, all of it multiplied by a squared, just as it should be. So this gives us quadratic shift in frequency with amplitude. And finally, for the third order displacement as a function of time, we write a to the power of 3 divided by 16 omega naught squared times alpha squared divided by 3 omega naught squared minus lambda divided by 2 multiplied by cosine 3 omega t, which is the third harmonic generation. Obviously, as we go to higher and higher orders, these additional effects go as higher powers of A, meaning that they become less significant with smaller amplitude of oscillations, and vice versa, become more significant with larger amplitudes of oscillations.